Come light it up, I'm ready to go. Come light it up, come light it up, I'm ready to go. Come light it up,
Thank you, Monica, for that warm introduction. Hello and welcome everyone to this talk where I'll be talking about how to optimize for both query latency and flexibility using Apache Pinot and Trino. So hi, I'm Chinmay Soman. I'm currently part of StarTree, which is building the next generation real-time analytical platform on top of Pinot. Previously, I led the streaming platform team at Uber, and I am also part of some open source projects like Pinot and Samza. So before I even begin, I wanted to call out the awesome work done by these two gentlemen, Xiang Fu, who's actually the co-founder of StarTree, and Elon Zole, who's an awesome engineer in his stealth mode startup. Most of the technical work behind this talk was done by these two folks, so I wanted to give them the kudos they deserve. All right, so today I'll begin by discussing the modern complex analytics ecosystem and what are the key challenges of running analytical queries in this kind of when data is flowing across all these different systems. We'll look at how the hybrid architecture using Pinot and Trino can be used to overcome these challenges. Next, we'll look at the internal details of the Trino-Pinot connector, and then finally touch upon some of the future work that's happening in this area. All right, so let's begin. Here's our generic user application. This could be a mobile application or a website or microservice. Anything that is constantly generating lots of things like business events or logs and metrics, and that's being pumped into some sort of a streaming system, for example, Kafka. These applications also generate entity data, for example, user profile, customer profile, financial transactions, which need to be handled by a special purpose OLTP database, for example, MySQL or Postgres. And from here, data is constantly being archived into what we call as a data lake, which is used for all different kinds of analytical use cases. For example, powering your warehouse or running machine learning pipelines and reporting and so on. And in addition, a subset of this data is also captured in another specialized OLAP database, which is used to build real-time analytical applications. Now, interestingly enough, you could actually run analytical queries on any of these systems. But for the purpose of this talk, we'll actually focus on these two systems, the OLAP database and the data lake. And of course, there's many challenges of running analytical queries in this kind of ecosystem. But again, we'll focus on two in particular, which affects these systems. The first one being query federation. This is where you want to run a SQL query and then process, as part of that query, be able to process data which is sitting in both the OLAP database as well as the data lake. Now, users often choose this configuration because each system is optimized with a different purpose in mind. So, for example, with an OLAP database, you get access to really fresh data. So you can analyze data as soon as it's being produced. Typically, the query latency is super low, in the order of milliseconds, and also gives you a very high throughput. And on the other side, the data lake is great for managing large volumes of data. So think of like terabytes or petabytes of data in a cost-efficient manner. So typically, users would choose their most important fact tables that they want to analyze in real time and store it in the OLAP database, and everything else is stored in the data lake. And so the challenge is, how do you process all this data in a seamless manner? So this was one such challenge that the folks at Citibank were facing as part of doing their market risk analysis. This is the use case where they were trying to monitor adverse movements in prices, rates, market volatility, and so on. And all of that had to be done in near real time. So think of seconds of, or maybe lower single-digit minutes of when changes happen in order to limit the risk exposure. For this use case, they also needed the queries to be flexible because there were frequent changes in the business logic. And more specifically, there were lots of joins between the real-time fact tables and the slow-moving dimension tables stored in their data lake. In their case specifically, they were using HBase and SQL Server. And there's actually a great talk by Valentine on this topic that I highly recommend to go and watch. Another challenge with respect to these systems is the query complexity. Now, keep in mind, the OLAP databases, although they are great at giving or enabling very high throughput queries with low latency, most of them were not built to be ANSI SQL compliant. So very recently, some of these OLAP databases have started to support query semantics like joins, and still not really that mature. On the flip side, the data lake with the corresponding query engines, they're able to handle any kind of complex queries seamlessly across all the data that they manage. But with this particular option does not give you the low latency and throughput that some of these applications are looking for. So let's take an example. This was one such use case in Tenex Banking, where they wanted to enable product personalization for their customers. So things like how do you do dynamic fees or rewards, or let the users know how their behavior is affecting the rewards or penalties, and then of course capture the loyal customers and reward them. Now, keep in mind, this is a user-facing analytical application, which translates to we need to execute high throughput analytical queries, and the query latency needs to be really low. So in this case, they needed something that would give them the power of the OLAP database, but also be able to run these complex queries, including joins. Again, a great talk by Stuart. You should go and watch if you have time. So these are just some of the examples of the query complexities, and clearly we're missing something in this picture to support such use cases. And one such solution is to use Trino and Pinot together to run such queries. So before I go into the Trino Pinot connector, let me give a quick overview of these individual systems. Beginning with Apache Pinot. So for those who haven't heard yet, Apache Pinot is an open source distributed columnar database that's purpose-built to ingest data from all kinds of different data sources. For example, you have your OLTP or stream or batch, and make it available for querying in real time. So some of the, and by real time, the more specifically user-facing analytical applications, which is its strength. Some of the largest Pinot clusters are able to ingest upwards of millions of events per second, and can easily handle hundreds of thousands of queries per second in the same cluster, while providing millisecond level query latency for such analytical queries. One important aspect of why users are choosing Pinot in the recent days is because of its ability to support upserts. So you could have duplicates or upserts or mutability in your real-time stream, and Pinot is able to handle those effectively and provide a high degree of query accuracy. This feature is actually especially important for banks and other financial institutions, which is why we're seeing a massive adoption in that vertical, specifically because of this feature. And last but not least, Pinot is an indexing powerhouse. So it comes out of the box with a wide range of built-in indexes that you can configure for any of the columns in your schema. So ranging from simple ones like inverted or sorted to like Bloom filters or even complex ones, for example, JSON indexes or geospatial indexes. One of the most important ones, of course, is star tree index, which is really a way of generating materialized view on top of Pinot. And as I mentioned, it's a distributed system. So in data, there's several components involved within Pinot. Data is spread out across what we call as Pinot servers, which is the blue boxes here. Within each server, data is laid out in a columnar fashion along with any of the indexes that you configure in your schema. Next is the Pinot controller, which is responsible for coordinating all the cluster operations, for example, data partition assignment or replica assignment, managing the routing tables, and so on. And finally, we have the Pinot brokers. This component is responsible for query execution. So when a human or an application sends a query to the broker, it will do a distributed scatter gather across the Pinot servers to process the query. So what it does is identifies which servers it needs to communicate with for that particular query, and then delegate the query processing to the server. Each server will then locally execute the query and then return an intermediate result back to the broker. The broker then compiles all these intermediate results and sends the final response back to the user. And Pinot is a mature technology at this point. It's being used in production by several big names such as Stripe, WePay, Cisco, LinkedIn, Uber, and so on. Next is Trino. Obviously, I'll keep this short, given most people here would be familiar with Trino. But Trino is a distributed ANSI SQL compliant query engine that's able to execute complex queries across various kinds of data sources. It's also a distributed system and has components such as coordinator and the worker. The coordinator is responsible for doing query planning and scheduling the tasks involved to process a query. These tasks are then executed on the actual worker, which does the final query execution, things like scanning, filter, join, and so on. Needless to say, Trino is also very mature and being used in production by all these big names that you see here, particularly Netflix, LinkedIn, Lyft, and so on. So with Trino and Pinot, this hybrid architecture allows us to do all kinds of things. For example, query federation across the OLAP database and data lake and other data sources included. You can run complex queries on Pinot via Trino. So whatever is the gap will be filled in by Trino. It still gives you the ability to do millisecond level query latency because of the optimizations that Pinot has to offer. And similarly, because of this Pinot-Trino connector, we can also run highly concurrent queries. So in the next half, we can look at the details of how this is being achieved within the Pinot-Trino connector. So these are the components that we saw from before, with the Trino components on the left and Pinot on the right. When we get a SQL query, the Trino coordinator, assuming this is for the data managed by Pinot, will first fetch the metadata from one of the Pinot controllers. And this includes things like the schema, table config, as well as the segment list. Now, segment is think of a segment as a small chunk or a subset of the data managed by Pinot. This includes the columnar, all the columns within the schema in a columnar fashion, as well as any of the indexes that you have specified. And these segments, again, are located on different Pinot servers. So with the segment list, the Trino knows which servers it needs to communicate with to generate the query response. So it'll take a look at the given SQL query and then figure out how it wants to execute this on Pinot. And there's actually two different options of doing this query execution. If the query is an aggregation query and something that can be pushed down to Pinot, the Trino worker will actually send it to one of the Pinot brokers for query execution. In this case, pretty much all of the work for the query processing is handled by Pinot broker and the corresponding Pinot servers. And only minimal work is done by Trino. In other cases where it's not able to push down the queries to Pinot, it will resort to doing raw data scans directly from the Pinot servers based on the segment list that I mentioned before. So let's take a look at some examples to make it a little more clear. So this is one example where we are doing an aggregation query. We're doing a sum of column B from table with a filter predicate where C is greater than 10. There's also a group by clause here, group by A. In this case, Trino will determine this is an aggregation query and it can be pushed directly to Pinot. As I mentioned before, it'll just directly send the query to one of the Pinot brokers, and then do minimal processing on the response that it gets from broker and returns it to the user. So this is really powerful, and it supports the aggregation functions mentioned here, such as count, sum, min, max, and so on. And the reason it's powerful is because here we're leveraging all of the indexing and routing optimizations that Pinot has to offer. So, for example, Pinot broker can, given the segment list, it can automatically prune some of the segments that are not relevant to the query processing. And at a server level, it can utilize any of the indexes that we mentioned before. So all of this can actually give you anywhere between 10 to 100x latency improvement as compared to a regular Trino query where we are scanning all the data. Let's look at another example. This is a much simpler query where we are simply doing scans of two columns A and B with the filter predicate as shown here. As I mentioned before, this is something that Trino will actually resort to just doing raw scans directly from the Pinot servers. So this will obviously be in parallel. It'll fetch the data from the respective Pinot servers. But even now, it is pushing the filter clause directly to the Pinot server. So when the Pinot server receives this query, it can utilize the local indexes to minimize the data that needs to be sent over the wire to Trino. So for example, if you have a Bloom filter or a range index defined on column C, this will dramatically reduce the amount of work that needs to be done for running this query. So let's now take a look at a more complicated example shown here, right? So as you can see here, we are doing a join between two tables, table 1 and 2. The first part of the query is actually doing an aggregation query on table 1. And then in the second part, we are doing the join of the aggregated view with table 2 on certain conditions. So let's break it down. The first thing Trino will do is identify which parts of this can be pushed to the Pinot broker. So in this case, the first part, which is a simple aggregation with a filter predicate and group by, this is directly sent to the Pinot broker, and the result is obtained by the Trino worker. Next, the remaining part of the query, which is basically a scan of table 2 with a given filter clause, is actually sent directly to the Pinot servers. And then again, the intermediate response is obtained by Trino. And finally, the actual join happens in this case on the Trino side. So Trino combines the results from the two individual parts to finally create the final result for this joint query. So as you can see, we for these kind of complex queries, Trino will identify opportunities to optimize certain parts of the query. And where it cannot optimize, it will resort to data scan and then do final processing on the Trino side, which is again gives you the flexibility that you want from these two systems. So this is just a quick benchmark, again done by Elon and team. So thank you for them. I won't go into the details, but this is a data set of 40 million rows. And the queries being run as part of the benchmark were mostly aggregation queries with group by and filter predicates. And the two things that we are seeing here, the blue gives you the query latency for when aggregation is enabled, aggregation pushdown is enabled. That means the query is actually executed by Pinot instead of Trino. And the red or the orange blocks are showing the query latency when the data is just being scanned from Pinot and then aggregation happens on the Trino side. So if you can see here, on the x-axis is the total number of rows scanned, which is defined by the filter predicate. So as your selectivity becomes lower and lower, you actually need to scan a whole lot more data to execute the query. So as you can see, between 1 million and 39 million, Trinos actually has to scan way more records, do more work for running that query. And it's natural that the query latency just keeps on increasing. On the other hand, if you look at the Pinot latencies in blue, they're relatively flat. This is because even though the total selectivity changes, it can still use its even if the total data set that it needs to process changes, it can still use its routing and indexing optimizations to prune most of the segments or to ignore most of the rows and only focus on the ones that are relevant to that query. So with this combination, right, we're still sending a Trino query, but we can, as you can see, there's like multiple orders of magnitude query latency difference between the two techniques, which is what gives you both flexibility and query latency. All right, so now let's look at one of the cool things that happened as part of this connector. So as I mentioned before, you can the Trino connector tries to push down as much as possible to the Pinot layer, right? The goal is to do minimal amount of work. In some cases, there are things that Apache Pinot supports, but are not really currently supported in by Trino itself. For example, theta sketches is one example. So here's a theta sketch query example, which is actually a Pinot syntax. Theta sketches, in case you are not aware, it's a probabilistic data structure used to give you approximate aggregations. So with this enabled in Pinot, you can run it directly on Pinot, but even there's no easy way to run it on Trino in the vanilla version. So what Elon and team ended up doing is to model this as a pass-through query. So if you look at the syntax here, the Trino query is quite simple. It's doing is select star from a table, and the table is defined as Pinot.default dot the actual query that we want to push down. So this is, in some sense, this is a hint given to Trino that I know this query can be executed on Pinot, send it directly to the broker, and just give me all the results that you get back from the broker. So this again is powerful because we don't, until the official support for this grammar exists across both the systems, you can continue to leverage the unique things that Pinot has to offer, without changing your SQL query engine, which is great. Right. Okay, so now let's look at some of the challenges that the team had to overcome when running this in production. So one thing we noticed is when the scenarios where Trino worker ends up doing a lot of scans from the Pinot server. For example, it's doing select star or select a bunch of columns with low selectivity. It actually causes a huge memory overhead on the Pinot server. And in certain cases, it can result in out-of-memory exceptions, and the server might end up getting restarted. This is obviously non-ideal because it also affects the other queries happening natively in Pinot. So a simple solution the team used was to introduce a new gRPC endpoint within the Pinot server. And through this endpoint, we can now stream records directly to the Trino worker instead of fetching them all in the Pinot buffers before the wire transfer happens. So now we can safely do all kinds of queries, including large scans on Pinot, without having to worry about the Pinot server going down. So this has significantly improved the production readiness of this connector. Now, let me go through some of the recent improvements that have happened in this connector since the last time Elon and Shang presented this. So recently, on the query side, the team has implemented the having clause support in addition to the group by support, which was already there. And also, new data types have been are now supported through this connector, namely JSON, which is great for ad hoc JSON processing so you can have JSON columns in your input data source and then directly query it through Trino and Pinot. And then other things like wire binary, which translates to bytes in Pinot, Boolean, timestamp, and the corresponding array types as well. And this is some of the future work that is happening right now, and you'll expect to see this in the open source soon. The biggest one is the Trino, the write model through the Trino Pinot connector. So all the things I mentioned before are how do you query data in Pinot through Trino. What's the other thing that Elon and team have done is to enable writing data into Pinot through the Trino Pinot connector. So you can write a DDL query to create or manage tables in Pinot, as well as insert data into Pinot. And this is something they have been internally running in their company for about a year, and they're getting amazing results. So I'm also excited to see this being finally merged so that other folks can start using it. The other big thing that's happening in the Pinot side, excuse me, is the native join support. So Pinot historically did not have a multi-stage query engine. So joins was difficult to do. We have recently introduced ability to do joins within Pinot. And this is obviously super flexible, but where this is really helpful is scenarios where we can accelerate query processing within Pinot. So for example, think of a scenario where you're trying to join two fact tables or fact and dim tables, which can be partitioned on the same join key. So if users are okay with that assumption and can we can lay out the data during ingestion, then we have the ability to execute co-located or partition hash join queries, so that there is very little data movement between the Pinot servers, and the query latency is extremely low, in the order of maybe seconds or even lower. So with this, the hope is, in addition to filter push down and aggregation function push down, we can also push down some of the join queries directly to Pinot. So with these scenarios, Trino would send the join query to Pinot, and other cases where we still want to federate data, we can still use the current mechanism that Trino has to offer. So this is an optimization that will only improve the query latency that we get from Trino and Pinot. So just to conclude with what we saw in the talk with combining Trino and Pinot through the Trino-Pinot connector gives us a lot of things, right? It gives us the flexibility to run ANSI SQL compliant queries on Pinot and get the results in real time. It gives us the speed by pushing down as much of the complexity to Pinot as possible. We can really power ultra low latency and also high throughput analytical queries. As a side effect, it also helps with cost. If you compare this with trying to simply do the processing in one system, the combined power of Trino and Pinot will result in a lower cost to serve in terms of the storage, memory, and CPU that you need. And finally, this gives us a lot of flexibility to federate queries across Pinot and all the other data stored in all the other systems as we saw before, which is amazing. With that, I'll conclude my talk and happy to take any questions that you have. Thank you.